My presentation is on the photocatalytic degradation of methylene blue dye, and it will be a scoping review of photocatalysts that have real-world applications. Methylene blue dye is a water pollutant which is present in wastewater discharges from many industries, such as textile, printing, paper, leather, and plastics. Water pollutants contaminate water bodies with harmful substances, and methylene blue dye is not an exception, as it is an organic pollutant that is toxic, non-biodegradable, and carcinogenic. It is hard to biodegrade using natural processes due to having a resistant aromatic ring, which has been synthetically engineered. Methylene blue dye is a model pollutant, i.e., it is used as a benchmark for studying and predicting the behavior and effects of other organic pollutants, which is mainly due to its toxicity and persistence. My scoping review aims to find a photocatalyst that is the most suitable to use in real-world applications by looking at commercial viability, sustainability, efficiencies, costs, and preparation processes. Efficiencies are found through the degradation rate and degradation percentage and are needed for degradation to be practical and possibly financially viable. This review is extended from Din et al., a critical review that had a broader variety of photocatalytic assemblies than other reviews due to not focusing on a certain type of photocatalyst, which consequently led to a larger number of photocatalytic assemblies listed, with coverage of many experimental factors, including irradiation times and degradation percentages shown for each catalyst. A strict inclusion criteria was needed as the photocatalyst had a large range of degradation percentages and irradiation times ranging from 18% to 100% and from 15 minutes to 4,320 minutes. The inclusion criteria were degradation percentages of above 90%, irradiation times below 180 minutes, and costs below $100 per kilogram that were estimated from e-commerce websites. The exclusion criteria were papers that were on photocatalytic degradation of other dyes that weren't methylene blue dye, and the degradation percentages and/or times not being listed. All of the photocatalysts in this review study are nanocomposites, with certain modifications that increase the degradation rate in the metal base. There were varying levels of sustainability, where 4 out of 12 were more sustainable, while the other 8 focused only on increasing efficiencies. Many titanium oxide catalysts fit the strict criteria. A possible distinction between these photocatalysts is whether the photocatalysts reacted under visible light, UV light, or both, which would affect how financially viable it is. Titanium oxide-based nanoparticles have high efficiencies. However, each has its own various limitations due to modifications of titanium oxide. The photocatalysts all have various synthesis processes and have different complexities and require different lengths of time to synthesize. Among all of the selected photocatalysts, the photocatalysts that are sustainable are more desirable where other factors, such as cost and efficiencies, are similar, although the materials could potentially limit the amount of catalysts produced, such as leaves. Across studies, iron oxide nanoparticles, which are sustainable and multi-purpose, as it also has antibacterial activity of E. coli, are magnetically recoverable and react under sunlight, are comparatively better than other photocatalysts. Another photocatalyst is titanium oxide graphene porous composites, which react under visible light with multiple applications such as hydrogen production, water purification, and air detoxification. They are easily fixed, recycled, and reused. However, the synthesis process is complex and takes over 8 days. Overall, iron oxide nanoparticles are the most desirable photocatalyst as the sustainability and multipurpose uses go beyond the single-purpose nature of copper of other nanocomposites. Photocatalytic degradation is not used in real-world applications currently, as there are challenges such as real industrial wastewater being complex and results isolating one dye not being always translatable. Cost, energy, potential harmful byproducts, and reaction conditions are some factors that could limit the uses of certain photocatalysts for dye degradation. However, many photocatalysts have reduced these limitations, with a lot of research being done, and sustainability has also been focused on. My scoping review has led to finding more possible feasible photocatalysts to be used in real-world applications.